So first we're going to take a look at domain and range and several variables. And why do we need several variables? Well, the short answer is that life is complex, and typically once we're out of the basic word problems, there's more than one variable in a situation. So a good example is the volume of a cylinder. The volume of a cylinder depends on the radius and height. As the radius changes, so does the volume. As the height changes, so does the volume. So volume depends on two different variables. So I can say there's another function, xy, and it depends on two things also. It depends on x squared and y squared. Now, when we were in algebra, we should remember the function f of x. So a lot of times we saw f of x equals x plus 1, or f of x equals 2x minus 2. F of x really stood for y. When we're talking in calculus, f of xy typically stands for the measurement of height in a three-dimensional plane that we call z. So that's one place we're going to have to adjust our knowledge base from algebra f of x is y to now in multivariable calculus f of x comma y is the same thing as writing z. They're synonymous. So this is going to be called a paraboloid. It's crazy, right? At above the point pxy from two coordinates of p. So I'm a visual learner. I want to know what does that actually look like. So I can do my f of xy, and I want to know what a paraboloid looks like. So I'm going to use this GeoGebra 3D calculator that I'm linking in the announcements to see what does that look like. And if you look at that, it's like a three-dimensional parabola bowl. So I could fill this bowl up, I could pour things into it, but it's forming a three-dimensional parabola. So that's kind of what we're looking at. It doesn't appear to be solid on the inside. It appears to be hollow based on the image that I'm given. So that's kind of nice to know, as that's what that actually looks like. So if another approximation, just another example of something that depends on multiple things is temperature. Temperature is going to have a lot of different things that it depends on. It depends on your geographic region. It depends on the time of year. It depends on the weather patterns. So it has multiple variable implications. And specifically in this course, we would talk about latitude and longitude, which are two different measurements. So latitude would be x and longitude would be y. So I could say temperature depends on f of x comma y, where x is latitude and y is longitude. So these are just examples of why we need multivariate calculus. So if I want to start talking about definitions, if I have a function of n independent variables, so n could stand for 2 independent variables, 3 independent variables, 4 independent variables, the domain is still going to be the input. That's going to be the values that I can input into the function. So that's why we're still calling it domain. And so the set of W values would be the values taken on by the range, which would be the dependent variable. So here, my independents for my domain are x and y, and my dependent is f of xy, or what we call z. So that's all this definition slide means. Domain and range is still input and output, but this time we have more than one input and only one output. So we're not really changing the game here. We're just adding a layer to what we already know. So if I have functions of 2 independent variables, we typically call the independent variables x and y. That's just a notation thing for us, is that independents are x and y, and then my dependent typically tends to be z. So as you can see, if I'm looking in this plane, the coordinate plane is typically x is horizontal and y is height. Well, that's going to shift a little bit as I look at 3 dimensions. As I'm in 3 dimensions, x and y are dictating this flat plane. So anything that's in xy is in this flat plane. And then z is the height. So just to help you visually conceptualize what's happening, x and y are on the bottom part of that plane. So if it was a cylinder, then the circle portion of the cylinder would be in the xy plane, and the height of the cylinder would be determined by z. Okay, so that's the visual correlation between what is happening there. So how do we figure out domain and range? It actually doesn't change. So domain and range would be all real numbers unless we have something like a square root, because we know that square roots are not defined when there's a negative number. Or if I have a fraction, the denominator still can't be 0. So we haven't actually changed any of the variables here. The things are still the same. What's under the square root can't be negative, so y minus x squared has to be greater than 0, and xy cannot be equal to 0. And that's how I'm looking at my domain. So I'm not changing the rules of domain and range. The rules are the same, but this time I'm not going to have those nice brackets with numbers. I'm going to have variables in there because I don't know what it's going to stand for. So how would I write this up? Well, I can't have a negative number under the square root, which means that my y value has to be larger than x squared. If my y value is larger than x squared, then I don't get a negative number under the square root. Similarly, my range is going to go from 0 to infinity, because no matter what I do to a square root, I'm never going to get a negative number out of it. And then in the fraction situation, my domain would be all real numbers except xy is not equal to 0. Or I could say xy equals 0, or I could just say xy is not equal to 0. So you have two options. So all reals except when xy equals 0, or just xy does not equal 0. Because of that, my range will be broken up from negative infinity to 0, because I'm not going to get 0 out of this, and from 0 to infinity, just like if I had 1 over x. So compare this to 1 over x into 2d. Sign of any function, no matter how many variables there are, is going to be all real values for things I could plug in. I could put any number inside of my sign function, it doesn't matter. But I can only get out numbers that are between -1 and 1. And that's not changing from our knowledge of two-dimensional space. So here's a couple of looks at what it looks like for something if I'm looking at the actual domain. So what this picture did is it took the domain of this big function here, and it's zooming in on that bottom axis. So I'm very visual, so I want to know, what does this function actually look like? So I'm going to go in here, and I'm going to type in, and if you look further down, there's actually a calculator window in here. So I'm actually going to, I need to first get my fraction. And to get your fraction, you just hit the divisible line. So this equation is x plus y plus 1. And that's going to be over x minus 1. So let's see what that looks like. That looks pretty crazy. And so if you look at this region here, right here, there appears to be an asymptote, and from this blue dot down is going to be a height. And then same thing here, from this blue dot up, it's a height. So I've got this asymptote relationship, but here is, and I'm hoping you guys can see my mouse, here's the trapezoid that's flat in the xy plane. So this is my x, this is my y, and this is what is in that plane. So it's this flat trapezoid. That's where this image is coming from. And if I were to find the equation of this line, it would be where x plus y plus 1 is 0, because there's 0 height. So I would say x plus y plus 1 equals 0 because there's no height involved there. And then I would have x minus 1 would give me this line right here, which kind of gets close to measuring the width of that trapezoid. Another example would be this graph right here. If I'm looking at the domain of this graph, it looks like it's all real numbers except where the bounds of this parabola are, which should make sense because my natural log cannot be 0 or negative. So I need y squared to be larger than x. So I need y squared to be greater than x. x if I'm looking at this from that perspective, so that I don't get a 0 and I don't get a negative number. So where y squared is greater than x, let's think about back to our 2D stuff. I would graph the equation x equals y squared, and I would shade everywhere that y squared is greater than x, which would be outside of this, because if I plug in the number 5, I do get that, if I plug in the number, let's say 5, 2, so I would get 2 equals 5 squared, it's greater than, so I would shade it. So this goes back to inequalities and shading. Another example is 9 minus x squared minus y squared. So at first you might go, well, wait, why is this x squared plus y squared? That's because I need 9 to be larger than x squared minus y squared. So when I put the x squared and y squared in parentheses, I have to factor a negative out. So it becomes 9 minus x squared plus y squared. So I need 9 to be greater than or equal to x squared plus y squared, because I can take the square root of 0. If it is equal to, it's this shaded line on the outside of the circle. If 9 is going to be greater than that, that means that x squared plus y squared needs to be smaller, and it needs to be what's inside of the circle. So that's how we're getting the visual for the domain there. So if I'm looking at functions in 3 variables, it doesn't change the process. Under a square root, I have x squared plus y squared plus z squared. I'm going to ask myself, is there ever a time that that's going to be negative? And the answer is no, because I'm adding numbers that are squared. So my domain, instead of saying all real numbers, is entire space. My range is going to be just like the square root of x. My range of the square root of x is 0 to infinity, because I'm never going to get a negative number out of there. So it's really just adjusting the same thinking that you were using previously. If I had 1 over x, I know that the domain would be x can equal 0. Well, I have x squared plus y squared plus z squared. Those can't be 0. And in this fraction, I'm not going to be able to get negative numbers out of it because the variables are all squared. And I can't get 0 because 1 divided by something is never going to equal 0. So my range is 0, infinity. And then for the natural log, x times y, that's all reals. The problem is that you cannot plug in a negative number or a 0 into the natural log. So I know that z has to be greater than 0. And that's going to be considered a half space because that's halfway on the number line. So that's why we're saying half space, is because if I were to take the number line and divide it by 2, it would be 0 to infinity and then negative infinity to 0. So z is greater than 0 is half the space, literally. And the range, I can get negative numbers out of a natural log. So if I was looking at the range of natural log x, that would be negative infinity to infinity. It doesn't change based on having more variables. So in my YouTube channel, if you are a little rusty on domain and range, I would suggest going and searching domain and range and watching how domain and range are calculated with 2 variables, and then coming back to this PowerPoint. So if you search domain and range, you should be able to pull up a couple of different videos that I use in my algebra classes, and that'll be helpful as you continue to connect. The principles are the same. There's just more letters and the limitations, okay? So stay tuned for the next lecture. Work through these one at a time, process them, and take your time.